redefining carbon dioxide from pollutant to valuable product. SwRI is producing graphene from CO2. Graphene is used in electronics, batteries, coatings, biomedical devices, and more, creating a resource with unlimited potential while reducing carbon emissions. That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast, presented by Southwest Research Institute. From deep sea to deep space, we develop solutions to benefit humankind. Transcript and photos for this episode and all episodes are available at podcast.swri.org. Share the podcast and hit that subscribe button on your favorite podcast platform. Hello and welcome to Technology Today. I'm Lisa Pena. SwRI scientists and engineers have developed a process to turn industrial CO2 waste into graphene, a resource with unlimited potential. Tough, flexible graphene has a wide range of uses, including electronics, energy, biomedical, and construction applications. The SwRI process to convert carbon dioxide into graphene demonstrates how carbon capture can yield a useful and profitable material. We'll learn more about carbon capture coming up. Our guests today are SwRI chemical engineer and manager Michael Hartmann and scientist Miles Salas. They are leading this innovative research. Thank you for joining us, Michael and Miles.
Thank you for having us on.
So this is an intriguing process, taking carbon dioxide waste, which is carbon that has been captured to reduce emissions, and going a step further, not just storing it to keep it out of the environment, but using it to create a useful, profitable resource. We're excited to learn all about it today. Let's take it back to chemistry class with some definitions that will be helpful during this conversation. So I wanted to start with allotrope. What is an allotrope?
Okay, so allotropes are different forms of a same element. So when you have an element such as carbon, phosphorus, or sulfur, depending on the environmental conditions, they will form into different structures. So a good example would be with carbon, we have diamond, we have graphite, we have graphene, we have carbon nanotubes. There are many different allotropes. Most of your nonmetals are going to be the elements that have different allotropes. Metals do have them as well, but you get into the weeds there.
All right, so graphene is a carbon allotrope. Where can you find it in nature?
So graphene exists in nature just about anywhere where you can find graphite or any kind of carbon minerals. It forms just under typical processes, heat, pressure, time. With graphene, though, an easy way to think about graphene is that it is like a Lego. So it's a big flat sheet of carbon atoms bonded in a hexagon structure. And if you take graphene and you stack a bunch of them on top of each other like Legos, you can form graphite. So graphite you find in your pencils and other writing utensils. If you take graphene as well and roll it into a tube, you can form carbon nanotubes, which is another really popular science material that's being studied and researched a lot right now.
Okay, so when we are using those number 2 pencils, we are writing with graphite.
Yes, correct.
Again, graphite, graphene, very similar terms, but graphite is layered graphene.
Correct.
Okay, so how is graphene used?
Okay, graphene is depending on the structure of the graphene. So with typical graphene, most people imagine it in the shape of just a large flat sheet, like a piece of paper. But typically in production, depending on the way you make it, and that's kind of stepping into a little bit later, but depending on the way you make the graphene kind of dictates where you can use it. So large flat sheets of graphene are really useful for applications like sensors, thermal management, or like electronic interfaces because graphene is very conductive. So one application that I've seen them try to be used in right now is touchscreens. And then the other form of graphene that we can have made by different methods is called platelets. So rather than having one big, large sheet of material that's very thin, the process forms a bunch of little platelets that are like little specks that are a couple layers thick or one layer thick up to 10 to 20 layers thick, depending on it. And those materials also have very good electrical properties, and they can be used in composite materials, so you can add it to like plastics or other things as reinforcing materials, or if you want to take advantage of its electronic properties, you can combine it into like an electrode material to make poles for like a battery, like anode cathode materials, electrodes.
Okay, so many varied uses for graphene. Again, biomedical devices, sensors, electronics, coatings, lubricants, batteries, the list goes on and on. So how is synthetic graphene currently produced?
There are two main methods right now that are currently being used to produce graphene. There's many more, but the main two methods can be divided into those two categories. So you have your deposition methods, which is going to be like chemical vapor deposition, where you take a carbon feedstock, usually in this case it's methane, CH4, and you heat it up and ionize it into a plasma, and then you have this carbon gas plasma deposited onto a surface, and that surface will automatically rearrange into a graphene sheet, and that's how you can make your nice big sheets of graphene. But with that application, it requires extremely high vacuums and extremely high temperatures, so it's not something that is easily scalable. And the other main way to make graphene is through dispersions or exfoliations. So with this process, you take your graphite feedstock and then you run it through either electrolysis, or you put it in an ultrasonic bath, or you put it in some kind of liquid medium where you force a chemical or electricity to squeeze between those layers and push them apart to make the graphene sheets. In the dispersion process or the exfoliation process is where you'll see your little platelet-style graphenes.
Okay, Miles, thank you so much for that overview of graphene. I feel like we understand it better. And Michael's going to take us through this next question. So we want to learn more about the SwRI process to produce graphene. How does our process work, and how does it improve upon traditional methods?
Sure. So the main reaction in our process uses magnesium, which is just a solid metal at room temperature, and CO2. So magnesium is typically the solid material, and when you heat it up, it creates a melt, essentially. So we're at a reduced temperature from some of the topics Miles was talking about, the other methods. And in that melt, we're basically bubbling CO2 through there. So think of if you have a fish tank and you have a little gas sparger in your fish tank, little bubbles like that are coming up through this metal molten melt. So at the surface of these bubbles, essentially, there's a reaction taking place between the CO2 and the magnesium, and it's creating this magnesium oxide, and a carbon material on the, basically a layer of thin carbon material on the bubble. So that's where our process is coming in to form and create that graphene. So we're changing things such as temperature, flow rate, and a few other parameters so we can target different forms of carbon material being deposited on that layer. And graphene is one of the main ones we're really targeting. So in that process, there's a lot of different carbon analog materials getting produced, and our focus is to optimize that process to make just a single layer of graphene. So in this process, we have like 2 or 3 different materials in this melt. And at the end of it, we cool everything down and we take it to a digestion step, which basically just means we put a acid solution in there and create a salt from the magnesium, and the carbon is left over. So we do a few washing steps after that, and then we're left with a final carbon material. And there's potential for a few downstream purification techniques if we need them to get it into the right format as like a dispersion. But ultimately, we're looking also at ways for our process to all these salts and other products we're making, how do you recycle those back in so we can reduce the overall waste and energy consumption of the process. So far, this similar process has only been done in some small lab settings that we haven't really seen too much commercial applicability yet. But a lot of these unit operations have very analogous industries that they could be in, such as for magnesium, for example, the steel industry uses molten magnesium for different allotropes of steel that they produce. So there's other analogous industries that we can take unit operations from and kind of tie them into this process scheme and essentially accelerate the commercialization of the potential process.
You were using this CO2 as a feedstock, and ultimately this is going to come from a carbon capture process. So we want to understand carbon capture because it's a key component of this recipe for graphene. So, what is carbon capture, and how does this process support carbon capture initiatives?
Sure. Yeah, so from a very high level, almost every process that creates like the day-to-day products we use, like fuels, polymers, plastic bottles, chemicals, even power, they require some form of energy. And this energy comes from heating and power generation, essentially. So in those operations, they combust gas. So you might have heard of fossil fuels. So they'll combust a fuel or a gas stream. And in that combustion process, you make byproducts. And one of those byproducts is CO2, carbon dioxide. And this is considered a greenhouse gas because essentially it mirrors a greenhouse for plants in your backyard, for example. So it basically traps heat in the atmosphere. So sunlight goes in, but prevents the heat from escaping back out. And this results in overall higher temperatures and what we're seeing more extreme weather patterns around the world. So carbon capture is a process by which that CO2 stream in the vent gas of some of these units can be removed in either benign forms like carbonates, like solid materials, or separated into a pure CO2 stream. And then typically it's sequestered in downhole well injections. And these are typically add-on to refinery processes. But you can also capture CO2 directly from the air, which is known as direct air capture or DAC. So it's another analog too. But ultimately, these processes are very capital-intensive endeavors, which really reduce the profitability of existing operations and reduce the corporations from actually putting these on their unit operations. So the term for carbon capture has kind of more broadly been expanded into CCUS for carbon capture, utilization, and storage. And our process kind of fits in that utilization portion. So how do you actually make value-added products from typically a stream that would be either sequestered or just captured and nothing else is done with it? So how can you actually make value out of that material? And that's kind of a part in our work that we find very exciting and very challenging. So how can you really utilize this waste stream and make it into materials that are actually very valuable and useful to other industries?
So to understand the value of the U part of the CCUS utilization, the S part, the storage, is the other alternative. So what happens when the carbon is just stored?
Yeah, ultimately, there's geological storage wells, and it goes underground, and it stays underground. I mean, there's monitoring programs in process. I believe there's only a certain amount of what's called Class 6 wells right now, injection wells for CO2. And ideally, those, permitting would accelerate quite a bit. But right now, those are mostly regulated through the government on the U.S. side. And it's a very long permitting process to get that done. So to find analogs to not just do sequestering and actually say, okay, we can capture and utilize some of the CO2 instead of potentially waiting for this permitting process, that may accelerate some of the deployment of capture technologies in itself. So I've said this to a few of my colleagues, but it's kind of like a chicken or the egg. So which comes first, getting the sequestering going or getting the carbon capture going? And you kind of need them both to kind of go at the same rate, essentially, because you need a place to store the CO2, but you also need the CO2 to store. And the utilization is almost like an add-on for a nice future marketplace where once those kind of two paths are going in parallel, you can take a slipstream or that full stream of CO2 that's getting captured and actually utilize it for some value-added products. because right now there's so many, I guess, nuanced regulations and things going on in the world that you have to have a continuous process stream going, essentially. And if you don't have that for utilization process, you're not going to be able to keep running the process. So having a consistent source of CO2, be it going to an injection well or something that you can just take a slipstream off of and build your process to, is essentially the next kind of step and path forward.
So it doesn't just go from carbon capture to utilization. You really need that storage step in there either way, but the utilization part yanks it out from underground and makes it useful.
Yes. So there are some nuanced applications. There's a lot of potential ethanol plants producers that have very high purity CO2 streams, and there's some potential applications there. But ultimately for the larger emitters, just from the scale that we would need to get sequestered, some of these utilization applications are not as large as the sequestered amount that needs to get and take place.
Are you able to produce other useful materials aside from graphene through this process?
In this process, like Michael mentioned earlier, the main product is going to be carbon allotropes. So we're going to be making graphene, we're going to be making a little bit of graphite, some amorphous carbon, potentially even some diamond carbon nanotubes. That's just the nature because of all of these allotropes of carbon are more stable than just having unbonded carbon. So having the carbon's just going to want to rearrange into the most stable structure. And with our process, having those bubbles is trying to promote graphene just because the reaction occurs at a interface. So that what makes, or at least we hope that the carbon is just going to form sheets on that interface. But there are applications. I mean, should we not be making graphene, there are applications for the other carbon allotropes. So graphite's used all over the place for electrochemical industry, writing utensils, pigments. Amorphous carbon is also used in structural reinforcement pigments and other things. So we do have applications of the other products, but our main end products of this reaction are carbon allotropes.
Now, you mentioned diamonds are a carbon allotrope. Are we going to be wearing SwRI diamonds?
Probably not. That would be interesting.
But fun. All right. Let's talk about, graphene specifically. We've talked about its value, its many uses. But why did you pinpoint graphene specifically, and why are you interested in producing this particular allotrope?
So the main reason we're interested in graphene, there's two facets of that, but one of the main reasons is that graphene was discovered 20, 30 years ago. So it's relatively new. It's been described in literature as far as like the 80s, but in terms of isolation, it was first isolated in, I believe, 2004. So not too long ago. So there's been a lot of research done on graphene, and if you want to deep dive, Wikipedia has one of the longest pages I've ever seen of anything on graphene. It's massive, and it has like 200 sources on the page. So there's a lot of stuff you can deep dive into from there from a surface level. But for us, it's basically the big applications and the fact that it's been around for almost 30 years and nobody can make it at production scale yet. So that's some of those production methods I talked about earlier. They can make high quality material, but methods like chemical vapor deposition are very expensive because they require very high vacuum, and scaling up very high vacuum systems is not a trivial task. And we're talking vacuum strong enough to evaporate metals. That's usually where CVD vacuum takes place. So you can actually take a solid metal and evaporate it at that vacuum level. And the same thing with the exfoliation techniques. There's issues with scaling those systems up from like making graphite. Like if you do an electrochemical method, you're limited by the size of your plates and your reactor system, and scaling that up, it's not a linear relationship. You can't just make a bigger reactor because you also have to have more contact area for your electrochemical cells. And the other reason that kind of ties into nobody's been able to make it is that because graphene has all these exceptional properties and everybody wants to make it, but nobody can really make it, the market for graphene is crazy. So typical chemicals you see are weighed or like valued at like dollars per ton in industry. So graphite may fetch anywhere from $100 to like $1,000 per ton, depending on the quality of material. But because nobody can really make graphene, bulk graphene production is usually valued in terms of kilograms. So that's 1,000 times smaller than tons. And I've seen dollar estimations of graphene materials in platelet form, which is what we're making, ranging from like $2,000 per kilogram up to $10,000 per kilogram, which means you're at a tonnage scale, you're looking at hundreds of thousands of dollars per ton or even millions of dollars per ton. So that's a pretty big driver.
All right. So no one can make it on a large scale. Is SwRI trying to change that?
Yes. So that's one thing we're trying to do. At least with this project, we're in the very early stages, but we do plan to start scaling up the process to try to bring it into a much larger scale. But one thing about this reaction is we're not necessarily limited by our reactor size, and the reaction itself should be very scalable, because that's what we're trying to show with this.
So what's the plan to scale it up?
Yeah, on our side, our scale right now, we are in the maybe about a 100-gram reactor size. So we're still relatively small scale. But when we were looking into this process, we were specifically looking at what other industries already have existing large-scale commercialized operations that we can apply. So our reactor technology, it's very basic. It's just a basically heated stirred melt reactor, if you call it that. So it's just electrically heated. But the kind of unique thing is, for our process specifically, is looking at some of the sparging dynamics. So how to distribute these CO2 bubbles in this reaction. So that's where some of the unique applications in design come into it. But the actual key large component technologies are almost all existing in commercial states. So we can just kind of take those and modify them as we need to prove out a scaled up process. So that's kind of our kind of next steps going forward would be, okay, how do we build this from the gram scale to the kilogram scale, like a factor of 10 scale up? Then once we kind of figure out those kind of micro versus macro, like flow dynamic effects, and how do we increase yield, efficiency, some of those properties we're looking at, how do you take that to the next level? So I would say typical new technology development that we've seen in the chemical engineering department for working with clients is anywhere in the 10 to 15 year range from a brand new process. Just doing the R&D, the scale up, the modeling simulations, even permitting, if you're going to get to that commercial plant scale, it just takes time. So for our process, just because there are such unique analogs out there in different industries, we're hoping to accelerate that, potentially cut that in half if we were to get the right funding sources and kind of clients to help take this technology to the next scale. That would be our kind of R&D path forward for what we're targeting.
And is the goal some sort of a pilot plant?
Yeah, so that's kind of our end goal. So right now we're very kind of single unit op in a batch mode. We're kind of taking one piece at a time, and that would kind of be our next step. How do we do an integrated kind of pilot unit, look at each step in a continuous fashion, so we can do each process step and prove out that you can do either a batch, semi-batch, or continuous mode, and how that would actually work, behave. And that'll help us look at when we get into kind of the more modeling aspects of a plant design. What does that look at when we're looking at the plant economics, the cost, the energy penalty, looking and integrating all of those together.
Okay, so the process demonstrates repurposing industrial CO2 waste, but does the process or the goal, ultimately the pilot plant, would that create CO2 emissions? You're capturing these CO2 emissions to get them out of the environment, but does the process to create something useful out of the emissions create emissions? And, how is the process powered?
Mm-hmm. Yeah, so that's a great question. So in our group, when we start evaluating CO2 conversion technologies, that's really one of the first things we look at. What's the energy penalty? Are you emitting more like CO2 than you're converting? And a lot of that's kind of sometimes referred to as a carbon intensity score. So you basically, you want to avoid using more energy than you're basically using to convert the CO2. So our process currently uses a high temperature melt reactor for the reaction to take place. And in this reaction, it is slightly exothermic. So once you essentially heat the reactor and get that reaction going, it is giving off a little bit of heat to help kind of keep the process going. But that said, there's still a melt that needs to take place and some energy usage. So most of our unit operations were kind of chosen to be electrically powered, heat integration with electricity essentially. So we have heaters, mixers, pumps, sonication devices potentially, and they're all using that electric power. So this is coming from the grid, just like you plug into an outlet in the wall. And it's the grid itself. I mean, we're making some assumptions here, but it's definitely getting more towards a renewable power, renewable energy. I think the city of San Antonio is about 14% renewable right now. So still low, but overall that's increasing every year, and there's more demand for renewable solar, those type wind, so those type of power generation sources. So that said, we're not expecting that we're not going to be going into this assuming we're purely 100% green power. But that's really dependent on where we would do a final plant location, because certain areas potentially do have that more renewable grid. So for the most part, we're kind of getting to that point of looking at that carbon intensity score. So we're working on right now a plant design, what we call a techno-economic analysis. So doing a process simulation of what a commercial or pilot to commercial plant would look at, and then how much would that cost to build and fabricate. And that would kind of look at that energy penalty score. But our full process is looking at full like heat integration systems. So for example, some of the sonication steps, they are they release a lot of energy, so they have to be cooled. So there's a lot of good heat integration techniques there we can use and apply that to some of the power sources on the front end side of the process. In addition to some recycle streams we're looking at integrating in. So ultimately, the short answer is we're still looking at that. I'll just say that for short. But it's definitely something that we want to get the data from the lab scale to be like, okay, what are the yields? What is the quality of product we're making? And then kind of look at that score of, does it make sense to go through with this as a waste stream? Ultimately, either way, if we can use CO2 and actually scale this process for such a high dollar value product coming out of it, there still may be a lot of commercial application to just not be as carbon negative as we would like it to be, depending on what heat integration may need to take place.
Okay, interesting. I wasn't aware of the carbon intensity score. Nice, an easy way to look at that. Wanted to talk a little bit about, environmental laws and regulations. How do changes in these laws and regulations impact your research?
Yeah, so new laws and incentives that have gone into effect recently have had really a major impact on our work. So recently the IRA, or Inflation Reduction Act, that was passed, increased what was already existing, but they increased what was called 45Q tax credits. So these incentivized carbon capture, utilization, and storage projects. So they essentially range from the government will give you a tax credit up to, well, it depends, from about $60 to $180 per ton of CO2 captured, depending on the source and end use of that CO2. So it's a very broad range depending on the technology, but that has definitely increased in the amount of CO2 capture, utilization, storage. All those projects has kind of taken a very sharp turn up just because of that passing of that law. That said, there's also in that law 45V credit, which is for clean hydrogen production. So there's a lot of unique applications there, but a lot of it is just getting that tax credit so you can actually make a captured plant more economically viable. So in our world, we've seen kind of these incentives spur more R&D projects in the chemical engineering department here at SwRI. And there are also net zero goals that are put out by DOE, as well as the Paris Climate Agreement and they both kind of have net zero targets by a 2050 date. And kind of while these are just targets, they really do outline what needs to be done to kind of take care of the emissions problem that's occurring. So I just wanted to give like kind of a real example of how laws, regulations, and agreements kind of working together kind of can actually work. And it's not all doom and gloom in kind of that area. So in the 70s and 80s, we had a lot of ozone depletion issues because of some of the refrigerants, solvents, and kind of CFCs, some really bad components that were used at the time. And in 1987, there was the Montreal Protocol was passed, and that was basically a kind of to help eliminate the usage of these materials. And in 1990s, basically the U.S. Congress passed or amended the Clean Air Act to help give the EPA authority to kind of regulate these and eliminate the usage. And worldwide, since kind of that time, with a lot of different countries putting that in, the usage of those I think went down to about like 99% from the level it was at then. So barely any usage anymore. And those ozone holes have started to close up. And I think the last I saw was about by 2040, we should be at the 1980s level. And they're looking at potentially having it completely closed by 2060. So that said, it's not
good progress.
It's good progress, but that's just showing that's what a good 80 years before the problem really gets to the point where it's back to levels it should be now. So it's not a short-term process by any means. And it's kind of the same with the carbon reduction efforts that we're starting to see take place. So this is really an issue that I would say our generation has been tasked with to start it kind of now and keep it going, and it'll keep going for generations down the line because it is a very challenging aspect to kind of try to mitigate because there's so many different industries and so many different emitting sources. So it's not a one-size-fits-all solution. So that's kind of what we've seen in our work is there's a lot of different areas and they're all going to be needed together to actually come together and actually mitigate the emissions that are in all of these different industries.
All right. So sometimes laws and regulations boost your work, are helpful, and really can help the world.
Yeah.
Yeah. Okay. So any roadblocks or challenges to making your process commercial?
Yeah, so our goal when we looked at this specific reaction and building it into a larger process was to use as much existing industry processes as possible. So like I kind of mentioned earlier, melted magnesium is used in the steel industry to make different alloys. So there is existing equipment and knowledge there. A lot of downstream separation steps we're proposing are used in chemical industries. So those are existing. And I think one of the key challenges that we really see with our process is kind of putting these different unit operations together in a continuous or semi-batch fashion. And that's kind of what we see the next steps as kind of the integrated scale-up process for us is how to actually put these more unique applications together in one area where they haven't necessarily been done or tried before.
And overall, what do you envision for the future of your work? You know, future clients, how soon are we talking? You mentioned maybe 10 to 15 years?
Yeah. So short term for us is we want to finish that techno-economic analysis and carbon intensity score to really understand what the process looks like at a larger scale. And then, longer term would be to continue some of that R&D effort to look at a scaled up process, to look at some of these micro macro effects of mixing and bubble dispersion in some of those areas. So in I'd say the chemical engineering department, we really specialize in that scale up from lab to pilot scale, which is what we'd see as the next steps. And we're really looking at, after we kind of get that all put together, looking at clients to help either license the technology or help us scale if we find the right partner. And like I mentioned, timelines are very challenging from a number standpoint because there's a lot of facets that go into those technology development areas. So a lot of it is looking at the end goal targets, and we think this is a very viable commercial process that could get it to the next stage here. But it's really just finding the right partner to help reduce that, basically accelerate the deployment of the technology.
Who would be your ideal first client or clients?
Yeah, so I'd say a lot of chemical industries, they're specifically looking at graphene as a additive material. We've seen actually some interest from CO2 capture sources, capture plants who have CO2 source and are asking what can we do with it. So a lot of not just U.S., but we've seen some interest in UK and actually Korean companies. But a lot of them are in materials manufacturing companies, for example. So like Miles kind of mentioned, a lot of electrode manufacturing. Those are kind of like probably the key customers we'd end up looking at.
Okay, and we want to end here with a question for both of you. What motivates you to push forward with this research?
So for me, being able to be at the front of science, so almost all the work we do is like cutting edge research. So being able to be on that forefront and work with people that are on that forefront is what keeps me coming into work every day. It's pretty incredible. And then another thing, at least from an environmental standpoint, is sustainable process are critical for moving forward as humanity. At least that's the way I see it. Because we only have a finite amount of resources given to us on this planet. So being able to efficiently reuse and recycle them or kind of loop them around is, I think, what we need for the future.
Yeah, so personally, I find the research in this area extremely rewarding and interesting. So we get to explore these new specialty materials, like Miles mentioned, first of its kind technologies, and we get to use what's considered a waste as a feedstock. So it's just really like interesting and nuanced to be able to kind of jump into those sort of topical areas for processes. So in our department, we are involved basically in all aspects of decarbonization and sustainability work. So we do biomass conversion, waste plastic upgrading, hydrogen production, carbon capture processes. So, and we're helping, how can we look at ways to reduce this energy, utilize waste streams, make cleaner burning fuels, for example. And this is really just one process that we get to explore in our section with carbon capture, carbon utilization. But it's really exciting to find these new ways to reduce emissions and a positive impact on the environment and our future. So we have a vision at the Institute set forth by our founder to perform research and advance technology for the betterment of mankind. And I think the work that we're doing right here really embodies that message. So embodies that message by finding economical solutions to challenging problems that affect essentially all of mankind. So it's not just a one area of the world that we're solving a problem for. It'll help benefit everyone and not just a single entity.
All right. Really great answers. Again, you said you're at the forefront of science, sustainability for humanity, the exploration aspects, impacting the future. So many benefits to your work and research, from reducing carbon emissions to producing useful, multi-purpose graphene. The process still under development, but it really holds so much exciting potential. So thank you for sharing your work and joining us today, Michael and Miles.
Yes. Thank you.
Thank you.
And thank you to our listeners for learning along with us today. You can hear all Technology Today episodes and see photos and complete transcripts at podcast.swri.org. Remember to share our podcast and subscribe on your favorite podcast platform. Want to see what else we're up to? Connect with Southwest Research Institute on Facebook, Instagram, X, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SWRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Pena. Thanks for listening.